We'll call the first method checkerboard measurement projections. Or maybe checkerboard measurement transfer might be a better way. Checkerboard measurement transfer. Let me explain this step by step. I worked at Disneyland Hotel Art Department for 3 years doing mostly paste up before Quark Express. And I did hundreds of photo crops. Any of you know what those are? You have a piece of tracing paper over a photograph and you have to crop it, and the photograph is bigger than it's going to be in the printed piece, and so you have to crop it proportionally. How do you do that? If you've got a square, it's, you know, the easiest way to make a square bigger or smaller, the quickest way, what is it? Run a diagonal from corner to corner, and if you do lines perpendicular to that, it doesn't make any difference how big you do it, it will always be a square. And if you've got a vertical rectangle and you need exactly that proportion, remember, if you're going to increase this 120%, the height is going to increase more than the width because there's more height that you're increasing. The quickest way to do it is run a diagonal, and it will always stay that proportion. No matter what kind of rectangle it is, a diagonal will keep your proportions the same. Okay? There's a reason for that. Diagonal lines is what this checkerboard is all about. I want to show you how it works, how handy that diagonal thing is if you were designing something like a checkerboard. Now, I'm not going to do a checkerboard because there are 12 times 12, and it would be too long for me to make lines up here. So we'll do one that has 3 across and 3 down. If we've got 3 equal divisions, important that they be equal divisions. Very easy to measure if you were doing it flat up there with the same 3 equal divisions. That should be a square, that should be a square. And you should get a square by doing that. And then you'd run those across. But that doesn't help us for the problem tonight of measuring back in space. But I want to show you what does. If you've got this proportion of divisions by 3s, and you want to measure 3 up, there's a way to do it that will be a key to how to do it in space. Run a it can go from that corner or that corner. It doesn't make any difference. And then what do? Where it hits there and hits there will be the same division whether you are doing this as a square or if you've got a vertical rectangle that you can divide into 3 that way, and you can run those verticals like that. What do? Run a diagonal across, and where it hits those will make proportionately, these were off, which is why you've got a distinction, but those will be proportionately the same as what these are. In fact, look at this. Notice that this is a thinner vertical rectangle, and this is a thicker one, wider. And notice that the same thing happened when I transferred it, that this one, that one is wider than this one, which is thinner, and this one, which is thinner. See, it has transferred those measurements. Now, say, how does that work in space? Do you remember last week when I showed you how if you draw an X on something that you can then transfer it, and if you imagine that you actually painted the X on the ping pong table, you could do that? Let's put this into perspective. Let's say horizon line is there. How can you measure this back into 3 equal spaces, or 5, or 7, or 18? Here's a way to do it. You can measure this, can't you? Because it's not foreshortened. It's a straight line that is not in perspective. And if you can get your ruler out and find that, oh, it's 13 inches. That's kind of a drag, isn't it? It's hard to divide 13 into 3 parts. But remember, these lines aren't foreshortened. If I simply go up a little bit where it's 12 inches, Can I do that? Yeah. There's a 12-inch line, and I can divide that, divide that 4, 8, 12. Now I should probably run a little line across there to show what I did. I divided that into 3. Now, if I run that division of 3 back to that line there, all I have to do now, those are perfectly spaced, or they should be. All I've got to do is run a diagonal, that corner to that corner, or the other. It doesn't make any difference, but watch what will happen. Where it crosses the lines will make the same division in space. In other words, I actually painted that flat on a board and put it in space, and there's no way it can change. I mean, if that line is painted on there with opaque paint, you tip it in space, and it's got to do the same thing. Does that make sense? Okay. Now we're going to apply it to something that gets a little bit more complex. It doesn't just work with equal divisions. It works with any divisions you want. So let's divide something into, I did it there on a flat plane that's lying down horizontally. Let's do it on a wall. Let's put a wall here. We need to get a horizon line. And let's say that we want that wall, it could be the side of a house, and in which case you'd have another plane over there. What we want to do is we want to make a division on the side of this house. Let's say that that's 10 feet back. Small house, but 10's a convenient number. 10 feet back, and we'll say that that's the 10 feet. And we've got something that divides, say, let's say there's a couple of quick divisions here. That'll make it easy. And we've got a couple of wider divisions here. We want to get those thin divisions here and those wider divisions here back in space. Now, here's the way we're going to do it. I need to find how to divide this space on a line that is not foreshortened. That is, I need to find it so that it was on a line. If we could tip this out, we'd see it not foreshortened. But all of these lines are foreshortened, except what? Yeah, the vertical lines are not foreshortened. Now, if I can take this trick, and somehow I've got to get 10 feet back there, well, that's going to be tough because it's in perspective. But I can divide this into increments of 10 by running this ruler along until I find where it says 10. And then I could just make little tick marks every inch, make equal divisions if I want to. There, I've made 10 equal divisions on that, which will all go back to that vanishing point there. I won't draw them all back because I want to make the point. Let's say that I'm going to make my quick 2 divisions like that, and then my thicker divisions there. Those are the important lines that I'm looking for. Now watch what I'm going to do. Throw these back to the vanishing point. I'll do this again, so if I'm losing you, just hang on. I'm going to explain this more than once. Throw those back to the vanishing point, and now what? Run a diagonal from this corner where I started down to that corner, and then I'm going to have these little magic lines which are taking this set of measurements, running it through there, and I will be able to divide this up in perspective. That was 2 small divisions, and then 2 bigger divisions which are further away, and so they seem to get smaller. Now, I know I went over that fast, and I'm going to repeat it again. Any questions about it? Because there's a couple snags in here that I want to go over this again so that I don't lose you with it.
Would it work if you did the other diagonal?
You mean if I did a diagonal from here to here?
Yeah.
It would give you those proportions backward. So the trick is, if you are going to do it from there to there because you like to do diagonals that go that direction, that's fine. But you need to do your measurements from down here. That ends up being the front corner. You're taking this line and tipping it in space. If you're going to tip it like that, you start your measurements down there. And now let me do this again, because I want to give you a series of questions to ask while you're doing it. It works when it's out of space, and it works when it's in space. I'm going to take this step by step and give you a series of questions to ask. First question: which line do you want to divide up in space? It can be this line, or it could be any line in between, but the thing is, you've got to decide which line do you want to divide up in space. And if it's not foreshortened, it's no problem. But when it's foreshortened, the problem is that you've got to get it out of perspective. This is the key to, you're trying to measure back that way. The only lines that aren't in perspective are these ones. So odd as it seems, you're trying to measure back horizontally. Odd as it seems, measure vertically. You want to divide this into 5 spaces. Thin ones there, thick ones there. Let's do it from the bottom to just show it can be done that way too. Measure along this line. If that line isn't convenient to your ruler, it's 17 inches. That's not convenient. What can I do? Project these out and make it 20 inches. That's convenient to divide into 5, right? Okay, I'm going to go every 4 inches. I said I was. I'm going to go ahead and do this equally just to make that point. Now I can run these back to that vanishing point. And when I found that, I don't care. I just used this line right there to find, because my ruler, it was convenient for my ruler. Once I've got that, I can lose it. These can be unequal. I mean, you can do lines like so and like so to get 4 thin divisions there, and then 3 bigger ones further on. Now, I did that backward, didn't I? That's okay. This will be the one that's closest to us. Now I will run my diagonal like so. See where it hits these lines, and then run verticals. And do you see what I've done? Closest one, closest measurement, second closest, middle, further away, further away, further away, further away. That turns into this block, this block, this block, this block, this block, this. It simply did that thing a diagonal does. It transferred. I used the checkerboard principle that a diagonal running through keeps consistent proportions to measure on a vertical line and then tip it back and then find all of the little key points. Did I lose you on it? Okay, so if you followed it, you're getting, your brain's starting to kick into gear for the next one. You know, this also works. I did this as a ground plane, but you know, you could just run these lines up and you'd find the divisions on a wall, right? We've learned that from the first evening. And likewise with this wall here, if I want to, all I've got to do is run lines off to that vanishing point where and I can transfer all of these measurements onto the floor. So if I'm trying to measure furniture back as to where it sits on the floor or people, and there's stuff in there that I don't want to mess with, I can measure it on the wall and then move it down. And I can get the other wall too if I want to, the far wall, and I can get the ceiling too, as long as I'm going back to that. So if you've got one plane, you can run those measurements around on a line system to find all of your planes. There's one limitation to this. You have to know the back edge. This doesn't work for that infinite regression, like, you know, telephone poles that are going off into infinity that 2 of the methods we used last week are better for, the vanishing trace diagonal and the diagonal finds far corner. You've got to know your front and back line to do this diagonal business. But there's one thing about this system that is the biggest inconvenience. There's too many lines. it makes a mess, doesn't it? I find myself tempted to stammer regularly because my mind is trying to go on to where those lines are and put this into words for you. Too many lines. But I wanted to show it to you, partly because this checkerboard principle can come in real helpful at times. When you're doing a tile floor, it's obvious. If you were doing a children's book of people who lived on a kind of chessboard or something, you would run into perspective problems with that, and you'd go for the obvious thing, is actually design a checkerboard and run diagonals. But it can help you solve these space problems. But there is one procedure that is better than any of the ones I've shown you. It's the most commonly used by architects. It is called, let me erase our title for the evening and label this number 2. It is called the measuring line and special vanishing point. Again, I put this title up here knowing that it doesn't mean a lot, but it will when I've explained it, because I'll go back over that title. The measuring line and special vanishing point. You saw how I wanted to measure this line, and it wasn't the right measurement for my ruler. There's many ways you could measure it otherwise. I mean, one of the things I found myself doing at times is to take a ruler that has millimeters on it and figure out how many millimeters that is, and then go to my calculator, and if it's 220 millimeters, 220 divided by 6 or 8 or 7 or whatever, and it'll give me a number, and then I can just count that many millimeters and make a tick mark, and I can divide it without having to do. But it's much quicker to just run this thing along until it fits. Oh, there it hit 10, or there it hit 9. It's easy to divide 9 into 3. Well, if you've got a line that is that long, and you want to divide it into 3 equal spaces, well, unfortunately, it's too easy to divide 12 into 3 equal spaces, and that ends up being 12 inches long. Watch me hit 15. Oh, I hit 15. How about that? Okay, let's see. 17 is not so easy to divide into 3 equal spaces. What is easy to divide into 3 equal spaces that's close to 17? 18 is easy to divide into 3 equal spaces, I hope. All you've got to do is run another line like this. And this has nothing to do with perspective yet. This is just a trick for transferring proportions. An 18-inch line is easy to divide into 3 equal spaces. 6, 6, and 18. That is perfect thirds. You know how to get it onto this line perfectly. Connect. This is the kind of thing you don't want to draw. You want to watch. Draw it later. Run line 18-inch over to line 17-inch. And then from this point, what do? A perfectly parallel line. It has to be perfectly parallel to this line, which you use a t-square for that. You use t-square and triangle. Don't do it freehand if you want it to be accurate. I can see I'm off already by a couple of degrees. Like that. And then you get your t-square and triangle and get the other one at that same line, parallel, and you will find that you divided that up into perfect thirds. And it does not make any difference whether this is 18 inches or what's another convenient measurement? 12 inches. Anything that you can easily divide up into 3s. Let's do this. Here is a line that is easy to divide into 3s because it's 12 inches. Now watch what happens. If you divide that, if you take that and connect it to there, a perfectly parallel line from this one will hit there. Perfectly parallel line from that one will hit there, and it will transfer the division precisely. Any question about this? Somebody started raise their hand. Change the angle of what?
The angle of the arbitrary 18-inch line.
You mean just change the angle of your ruler?
Yeah, to make it perpendicular.
And what I'm doing here is I am tilting this angle and finding a convenient measurement, then the parallel lines are a way so you can see what you did. And also, the reason I want you to see this is because this is what we're going to do in perspective in about 4 minutes. It works. Let me show you why it works. You say, well, it works with flat lines. That's great, Marshall. What am I supposed to do about it? Let's pretend like they're not flat lines. Let's pretend like we're looking at the top of a building here, or the top of a house. Okay? And let's say that this is the front of the house, and we want to make divisions, you know, where the doorway is. There's 2 feet, and then there's a doorway of 2 feet, and then there's 3 feet. We're making divisions across this helicopter view looking down on a house. Okay? I want to show you why this works not just flat, but in perspective. To keep it simple, let's just divide this thing in half exactly, which we know how to do because we've talked about it just about every week. There's the midpoint between there and there. Now watch what happens. I can take any line, any length, whether it's this long, and divide that in half, and then connect which end. I'm trying to transfer this line to that line. And if I run one that's parallel to that, it will hit in the halfway point. Say, okay, that's a nice trick. Watch. It works if I make a line this long. Let's just double this space right here. So whatever length that is, do it again. Okay, so I've got a division like that. And then transfer that to there. Now watch. Parallel line from this point should go right through there. Do you see what I'm doing? I'm going to do this in perspective in about 1.5 minutes. We're looking down on this, and here is the trick. I just made, to transfer these, I have made parallel lines. What's the principle of parallel lines? That if they get tilted into space, they converge where? At a vanishing point, somewhere either on the horizon or related to the horizon by a vanishing trace. So now, let's do this with a wall. Yeah, let's do it with a wall, and let's do it with 3 equal divisions to make the point. This is the wall of that house. This is that wall right there. I want to divide this into 3. I could do the checkerboard measurement and it'd be real easy with 3. Wouldn't be so easy if I was dividing it into 7 or 8 because I'd have to do a lot of lines. Here's a simple way. Find which line you're trying to divide back in space and pull it out of perspective any way you want. Turn it into a line like this that you can divide into 3. 15, perfect. Every 5 inches, I'll put a little tick mark, and I'll end up right there. Now, can you see what I'm going to do? Where is the vanishing or the horizon line on this? I have to have a horizon line to do this. These are parallel lines, meaning they converge right there. Every line that is parallel to that one has got to converge at the vanishing point, which means all I got to do is run a line from there to there, and run a line from there to there, and do you see what it did? It transferred these measurements into perspective, and I can raise them up there. I'm going to do it again, so hang on. Did some of you catch that? Okay, I'm going to do it again. I'm going to go a little slower, and I'll work a little bigger. In fact, here's the point I want to make. These lines from that to that, or from there to there, whatever, are parallel lines. If you take this thing and go like this, and tip it back in space, parallel lines converge. Let me do a different measurement with this again. Watch this if that other one didn't get you. I more or less did these lines. I could make smaller ones. I'll make bigger ones. I'll go 20 inches on this one. Now, 20's not easy. 21's easy to divide into 3. It doesn't make it, the thing is, it does not make any difference whether it's 21 inches, 9 inches, 15 inches. If I can divide it into 3 equal spaces or 7 equal spaces or whatever I'm trying to do, divide this line that's not in perspective. Now watch what I'm going to do. This is the crucial part. connect this far end with that far end, and it meets over there on the horizon. Meets with what? With the lines that are parallel to it. See that? Lands on the same spaces. I'll do it once more.